Prepare to descend into total madness. Not only does the Z80 out instruction not do what you think it does, but most documentation is actually wrong. Then the Amstrad CPC flips it on its head, and at the end, we may not even be able to use that instruction and instead need to use crazy methods. Welcome into a deep dive of the madness of the Z80 I. Let's start with a quick recap of how some CPUs talk to other chips on the computer. The simplest possible way that a CPU can talk to another chip is to simply have that chip listen for a particular address on the memory addressing space. For example, I could have the graphics chip listen on address 9000F. Whenever the CPU flashes that address on the address bus along with the write line, the graphics chip can read the data bus and interpret that as a screen border colors, for example. Just totally random example. Or maybe that's exactly how it's done in the VIC-20 with the 6502 CPU. That's actually super nice and a straightforward way to communicate with everything. Just give out addresses and document how each chip interprets the data. It also works beautifully to read data back from chips. Just do a read operation on that address and the chip can return some data in the data bus. The CPU is already set up for that. So this is great. Problem solved. We're done with the video. Well, not quite. So here's a memory map of the VIC-20 as an example. The area in pink is the address range reserved for I/O, and it's only 4 kilobytes out of the possible 64 kilobytes that you get with a 16-bit addressing bus, and certainly on a VIC-20 with only 20 or 32 kilobytes of RAM total, it will work without a problem. We have lots of room to spare. But what if you want to have 64 kilobytes of RAM without giving up 4 kilobytes for I/O? That's when things start getting interesting. The 6510 is the CPU on the Commodore 64. A lot of people just think of it as a 6502, and it's mostly true, except for a key difference that we care about here. The 6510 added a 6-bit processor port. These are 6 physical pins on the 6510 that are wired from the CPU to different chips. That way, the CPU can use those signals on those lines to talk to different chips and not waste any addressing space on I/O addresses. Those 6 new lines for the processor port are also handled in a very clever way. Instead of adding a new instruction on the CPU, they're simply mapped to the lowest 6 bits of address 0 to set the I/O direction of each pin, and the lowest 6 bits of address 1 for the signal on the pins. The problem is that you're a bit limited with only 6 bits, and while Commodore could have technically used that to address 2 to the 6 or 64 different ports on different chips, instead they mostly wire each line for a very specific purpose, so they can only control 6 different things. That means that a lot of the I/O still happens through specific addresses like CIA communication. And so we finally come to the Z80. Apparently, they decided that if you're going to have a 16-bit addressing bus, then gosh darn it, you better be able to have 64 kilobytes of real memory to access, and they didn't want to take any space with the I/O addresses. That sounds like a fantastic idea. The solution is very straightforward actually. Add a new instruction that signals that this is specifically an I/O operation and not just a memory read or write. And that instruction is called out. On a Z80, to write some data to a memory address, we could do something like this. That puts C000 in the address bus and 33 on the data bus, and then sets the write and MREC memory request signals. The rest of the system detects that and puts that address in the right location. Perfect. The out instruction functions the exact same way, except that instead of setting the MREC signal, it sets the I/O request signal. That simple. Except that I just lied to you, and that is not the right syntax for out. It's actually written out like this. Now you're probably saying, wait a second, that doesn't look like it puts the full value of BC on the address bus. Surely, that only puts the 8 bits from C, right? That would make a lot of sense, so let's find out. So let's have a look at the Bible of the Z80 programming, How to Program the Z80 by Rodney Zach. The contents of the specific register are output to the peripheral device addressed by the contents of the C register. Quick note from Noel from the future here. I actually missed that the very last line in there says register B supplies bits A8 to A15, so that's pretty clear right there. Okay, let's continue. So that seems consistent with the way the instruction is written, right? And how about a Z80 reference site? The value of B is written to port C. Yeah, that's pretty clear, right? So let's go to the source, to the Zilog documentation itself. The contents of register C are placed on the bottom half of the address bus to select the I/O device at one of 256 possible ports. The contents of register B are placed in the top half of the address bus at this time. Then the byte contained in the register R is placed in the data bus and written to the selected peripheral device. That is totally different. And why does register B come into play since it doesn't even appear in the instruction? So is the Zilog manual right and everybody else is wrong, or did Zilog mess the documentation of their own CPU? So I did what any sane person would do, and I wired up a minimal Z80 system. I know this is not up to Ben Eater's standards, but it was just supposed to be a quick temporary setup. This is truly a minimal build. I have the Z80 processor hooked up to a ROM and a simple program that simply does outCA with BC of FF00 and A of 33, and then it just repeats again. And actually, since the program is only 12 bytes long, I even only wired the first 4 lines of the address bus, and the rest are just going to ground. The initial intention was that you would step through all the instructions with this push button, and that when we get to the out instruction, the IORQ signal will be high, and you could see it in an LED, and then we would examine the address bus with LEDs as well at that time. However, after banging my head for many days on this, I remembered that the original Z80 processor cannot be stepped at a really low frequency. Apparently, it's implemented internally with some kind of dynamic refreshing, so unless it has a minimum frequency in the kilohertz, it will just not preserve the correct state. So you just simply can't do that. So if it's been many weeks since my last video, that's probably one of the reasons why. So now instead, I'm going to be driving the clock signal from this signal generator. I'm going to use something slowish, like 100 kilohertz. That will be fast enough that the Z80 actually worked, but slow enough that running on a breadboard with all the wires crossed and all that won't really matter as far as noise and crossover and all that. And here you can see the clock signal generated by the signal generator. And after I reset it, when we look at IORQ, there you go. You see that it periodically comes up like that. This is not ideal, but we can check out the address lines at the same time we're checking IORQ on the oscilloscope. And yeah, it looks like we're getting a 1 on every bit on the upper half of the address bus. And on the lower address bus, it looks like it's 0. So yeah, that seems to work. This would be a perfect job for a good data analyzer. And all I have is this cheap one, which the cheap part doesn't really matter as far as frequency because it's running really slowly, but it only has 8 channels. So I'm gonna hook up one of them to IORQ and then the other 7 to the middle of the address bus, maybe between A5 and A11. That way we see part of the lower half and part of the upper half. And yeah, there we can see the same thing. When IORQ is active, the lower half of the bus is 0 and the upper half is set to 1. You know what else would make this much more convenient to work with? If I had made this into a PCB with today's sponsor, PCBWay. Maybe it sounds weird to make a PCB for something like this. This is supposed to be a prototype, but this is setting up a Z80 with a ROM. That's something that you're going to be doing a fair amount. So it would be pretty trivial to turn this into a PCB design, upload it to PCBWay's website, and then I would get a simple PCB back in just a few days or a week at most. PCBWay has great prices for very small runs like that, so you can share them with other people, or maybe you can have multiple of them set up that way. That's actually a project that I may consider doing in the future. So if that's the kind of thing that you may be interested, definitely check out PCBWay.com. So this is great. We finally know what outCA does exactly, and the Zilog manual was correct. So now the big question is, why is the instruction written as outCA instead of outBCA, which is really what it's doing, and how come B isn't even mentioned in most of the documentation? The answer, I'm afraid, will cause us to go one step deeper into this mess. The answer is the instruction outI. Before we go there, I want to touch briefly into how to read from an I/O device on the Z80. We continue our parallel with reading and writing to memory. If we want to read from some address, we would do something like this. So it would make sense that to read from an I/O device, we would do something like this. Or, I guess, out AC. But I guess someone thought that it was too clashing to use the instruction out to bring data in. So they did exactly that and changed the instruction to in AC. Now, this is small potatoes compared to the mess that we're about to see, but it just bugs me that we have to use LD for load both ways, but then we have to go and use different instructions for out and in. And actually, that's not a horrible idea, so why not just ditch LD and go with a read and a write instruction instead? From a purely design aesthetic, that's just ugly having the way it is. But okay, fine. We'll have out and in. let's get to some of the really ugly stuff. One of the culprits of this whole mess is the instruction out I and its corresponding in I, of course. So let's warm up by looking at an easier to understand instruction, LDI. LDI is an instruction that will do several things. It will copy the byte pointed to by HL into the address contained in DE, and then it will increment HL and DE and decrement BC. And why does it do all of that? Because that way it can be inserted in a loop with BC as a counter and copy a block of memory from HL to DE pretty quickly. And as if that wasn't enough, the Z80 designers decided to take it one step beyond and implement LDIR, which actually implements the loop itself and continues copying until BC is at 0. I imagine for anyone who didn't grow up with Z80 assembly, this monster of an instruction is just a real eyesore. And I totally see that. And at the same time, I remember how LDI is so much more efficient than trying to do the same thing by hand. And since moving data around memory is just so slow and so important for drawing things on the screen, it does have a reserved spot in my heart. But yes, it's still really ugly. Now that we know about LDI and LDIR, I bet you can imagine what out I does. It does an out C with the contents of HL, increases HL, and decreases B. There's even a looping instruction, except that instead of calling it out IR, they called it OTIR. They really wanted to trigger my OCD. Anyway, let's do an example to see how that works. Say we have this code. So it will read the data pointed to by HL, which is the first byte in my data, which is A0, and it will do an out C with it. That means BC goes in the address bus, 03F7, and A0 goes in the data bus. Then it will decrement B. Since this is expected to be part of a loop, let's repeat it until B is 0. So it does another out, putting this time O2F7 on the address bus and B0 on the data bus. Since B is not 0, it does it again with O1F7 and C0, and now B is decremented, hits 0, and we're finally done with that loop. Did you notice anything there? We blasted several values to port F7, the contents of C, but the value of B was a countdown, so it was mostly irrelevant. So even though the Z80 puts both B and C on the address bus, only the lower byte is really intended for decoding the hardware. The fact that B is added to the address bus, I'm not sure if it's a side effect or to save on transistors, or maybe they're doing that on purpose to let some devices know about the countdown because maybe it will be important in some weird cases. But the fact that they named the instruction out CA just with C is a very clear indication that Zilog intended to address 256 ports, they even say that in the manual, and the value of B should be mostly ignored. And in fact, this is what happens in every sane Z80 system out there. From the ZX Spectrum to MSX computers, chips just look at the lower byte of the address bus to see if their address number has shown up. Confusing enough for you yet? No? The Amstrad CPC just entered the chat. Amstrad engineers decided that it would be a good idea to go against the normal use of the Z80 and, drum roll please, use the top byte of the addressing bus to access different chips. Why? We'll see that in a second, but let's have a look at what it actually means. Now you would do something like this, and it will use the F7 value stored in B to determine the port to communicate with. So really you don't need to load C at all, and you could simplify that to something like this, which makes it super confusing because the instruction names C, but we aren't even using it. Which finally leads us to what started this whole descent into madness. In my last video, I wrote this code. And it seems innocent enough, but I got swamped with comments saying that it was incorrect and it should have been out B, C. But now, finally, we understand why that code is so weird. It really is doing out BC, C, and on the Amstrad, which was the platform that I was writing about, it only cares about the B part. That's actually a very common idiom with Amstrad CPC assembly language, and you'll see it all over the place. There you're loading both bytes you care about, and then doing an out instruction right away. In that particular case, it's accessing the gate array and setting the screen to mode 0. Aha, some of you may be saying, that's why Amstrad made that odd choice. It's much more efficient to load all the values at once and then just do an out instruction than it would be to write something like this. It would kind of make sense, since each of those LD instructions takes 7 cycles, and an LDBC takes only 10 and takes 1 fewer byte. But that's not the reason at all, because you could have just used out CB and loaded BC the exact same way as before. The real reason for that odd choice that Amstrad made was something that Amstrad was really good at: reducing cost. Since we have a whole byte, that would in theory gives us 256 different ports that we could address. However, Amstrad decided to have the top 5 bits and use one of each of those bits for each major I/O system: gate array, CRTC, ROM selection, printer, and PPI. That was done that way so that each chip could have just one line directly connected to it, and the logic to talk to that chip would be trivial. The alternative would have been to have 8 bits coming into the chip, which would not be realistic and would require more pins that are available for a particular package size in the case of the gate array, or in the case of third-party chips, they would have to have external logic to convert those 8 bits into a single bit that would activate the chip. That would have made the computer significantly larger and more expensive. So that makes sense, but what does that have to do with using the top of the address bus? The answer to that is what we talked about in last video: memory banking. Remember how last video I mentioned that we had banks of 16 kilobytes and that we could detect which bank we're accessing by looking at the top 2 bits of the address bus? That means that the gate array needs to already be connected to A15 and A14, which are the top 2 bits of the address bus. If we were using the lower byte of the address bus for I/O, like a normal Z80 system, the gate array would need to have an extra pin or 2 just for that. So in this case, Amstrad managed to squeeze all of that in a 40-pin package by pulling that weird optimization. They saved some cost, and it made it so that all I/O on Amstrad worked completely differently to all other Z80 computers. And not only that, but out I and in I and out IR or OTIR are pretty much useless on an Amstrad CPC, because as part of the loop, B is going to be decremented, which is going to change the port that you're talking to. So they've killed about 4 or 5 instructions of the Z80 by doing that. Thanks, Amstrad. Okay, we finally made sense out of all of that. But there is still one big problem. The I/O space is mostly full. Check out this list for known I/O ports for different Amstrad extensions. They're a mix of original expansions and the newer ones. And each of them lists addresses and, most importantly, the bits that it cares about. And here's the big problem. Remember how I said that Amstrad used the top 5 bits? So if any of those bits are low, one of the 5 built-in systems will think that is being addressed. That only leaves 3 bits for extensions. And if we assume that we'll do a full decoding of those bits, that's only 2 to the 3rd or 8 different ports. That's it. And looking at that table, it looks like those ports are all used up with memory expansions right at the beginning. So what's a new hardware designer supposed to do if they want to make an extension for the Amstrad? Again, looking at the table, it looks like the answer is to also use the lower byte of the address bus. Yes, I know, I said that Amstrad wired only the upper byte, but I was talking about their own chips. As long as you have full access to the address bus, you're welcome to read any part of it and use it to trigger your own activation. And that's what people are doing for the most part. We'll see some interesting exceptions at the end. When you look down the list, you see that a lot of entries are taken, and what's worse, there are some extensions that claim a whole range of bytes to themselves. That might have been okay for the original board, but now, given how congested that table is and how easy it is to implement the bit logic on a CPLD, there is simply no excuse for a modern device to only do partial address decoding. So if you're making a device today, please confirm that there's room in that table and that you're only active when all the bits you've selected are active and no other time. Otherwise, you'll be running into constant conflict with other hardware, and I've seen actually several devices doing that. But even if you're well behaved and you're only triggered with one of those addresses, there's still only 255 possible ones. And the list is mostly full. To be fair, most of those expansions aren't going to be running at the same time, so maybe it's safe, kind of. Still, some hardware designers are giving up on I/O ports completely and finding alternate ways of communicating with the extensions. So you thought it was crazy until now? No, this is where crazy starts. All right, I'm gonna give you a problem and I'm gonna let you think about it for a second. So imagine you're an expansion designer and you have full access to the expansion bus, meaning the data and address buses and the usual control signals. How could you communicate with custom hardware without using IORQ? In case you're thinking this is purely hypothetical, this is exactly how the detonator is implemented. And the solution doesn't use any secret signals or anything that we haven't talked about. It's a really ingenious solution. So pause here for a second and think about it if you want. Okay, got it? Are you ready for the solution? The key to this communication is extremely simple. Sending some pre-agreed data pattern on the data bus, specifically the opcode fetch phase, which happens while M1 is active. That's it. If you agree that the byte to trigger the device is going to be, for example, C9, whenever the CPU fetches the next opcode and it's C9, the device can do its thing knowing, hey, they're talking to me. Yes, I can already hear the Z80 experts yelling at the screen. I know. C9 is the binary code for the read instruction. I did that on purpose. If we did that, the device will be triggered constantly by normal programs every time they return from a subroutine. So that won't work. We really need to find some data that will not be present in normal Z80 programs. Except that, look at that table. That is the matrix with every byte and what instruction it belongs to. No room in there, right? Well, not quite. Do you see those darker squares? Those are multi-opcode instructions. They're instructions that start with a byte, but then they'll have another byte that defines the full instruction. For example, for bit instructions, that prefix will be CB. And then we look in the second byte in the CB table, and if that was 1E, the instruction was RRE. How does that help us? Well, not all those tables are as full as that one. As a matter of fact, the MISC table is mostly empty. So the detonator in particular chose the FD prefix, which leads to the IY instructions table, followed by FD again, which is empty. Once the Z80 has started decoding an instruction like this, it needs to finish it. So it will actually ignore the second FD byte and keep trying to match the instruction in the table. That's why the detonator expects this instruction, which is FD 07 and then something. So the detonator is actually looking for the sequence FD, 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 and then the next byte tells it more information about what kind of operation we want to do. That's crazy! Depending how you look at it, that's either really clever, and I had never heard of this approach before, or a horrible hack. But the fact of the matter is that it works beautifully, and it avoids the overcrowded I/O table. The choice is really smart because clearly no well-written program is ever going to have the byte sequence while fetching opcodes. And also the CPU will not be interrupted in the middle of an opcode fetch phase, so there's no need to disable interrupts before sending any data to the detonator. The only possible downside is that the instruction has a side effect of storing B in some RAM byte, so you need to worry about where you point IY to. And then it's going to be a little slower than just doing out instructions, but it's really, really ingenious. And the good news is that if other expansions wanted to take that similar approach, there's a lot of room in that table to have hundreds or maybe even thousands of different sequences. I probably lost most of my hardware audience by this point with so much talk about software, but if you made it this far, congratulations. You have conquered the madness that is Z80 I/O, and now when you see out CC, you probably know exactly what it's doing. Or not. You never know. Better check those connections with a multimeter to be sure. In any case, I'll see you next time.